All right, today we're going to do chapter 5. And we're going to start with question 1. Question 1 gives some axes and some force vectors. Gives 4 axes and 4 force vectors. So let me sketch them out real quick. Okay. 7, 3, 2, 4, 5. So we've got like a 7, 3, 2, 4. So 7 newtons, 3 newtons, 2 newtons, 4 newtons, and 5 newtons. Okay? This one's got 6, 2, 2, 4, 3. So this one's got 6, 2, 2, 4, 3. 6, 2, 2, 4, 3. This has got 6, 4, 4, 3, 5. 6, 4, 4, 3, 5. Okay. This has got 3, 2, 5, 5, 4, 3. 3, 2, 5, 5, 4, 3. Basically, it wants to know in which situation does the acceleration A have a component in the x direction or a y direction? And then it wants to know in what quadrants they are. So to look at this, basically what we're looking at is we're going to see how the vectors balance each other out. So we're looking for what's called the net force. So the net force, or F net force. Net is what's left over after you balance everything out. So if I look here, this is 5 to the right and a total of 5 to the left. So the horizontals balance each other out, and we have 7 up and 4 down, so the net force here is 3 in the up direction. Let's look at this one. So I have 6 up and 6 down, so those balance each other out. I have 3 to the right and 2 to the left, so I have net force is 1 to the right. This one I have 6 up and 7 down, so there's more down than up. And I have 5 right and 4 left, so more right than left. So to me, this looks like it's 1 Newton down, 1 Newton over. So the F net is down and to the right. And this one here, it looks like I have 5 up and 5 down. Looks like 7 right and 7 right and 5 left. So this looks like it's, oh, just kidding. 2 newtons to the right. So the question asks, which have acceleration component in the x direction? So that'd be 2, 3, and 4 definitely have components in the x direction. Which have components in the y direction? 1 and 3. Did I do 4 wrong? Let me look at 4 again. 2, 3, 5, 5. Oof. I did. I drew it wrong. So this is wrong. Sorry about that. So I got 2, 3, 2, 5, 5, 4, 3. 3, 2, 5, 5, 4, 3. Okay, let's redo this one. So up I have a total of 5, down I have a total of 9. So I have an extra 4 in the down direction. Here, I have 2 to the left and 3 to the right and 5 to the left, which gives me 4, 2. Sorry about that. Let's try this again. So in the x direction, we have 2, 3, and 4 have acceleration component in the x direction. In the y direction, 1, 3, and 4. This acceleration is straight up, this acceleration is to the right, this acceleration is down and to the right, and this acceleration is down and to the left. So what are we missing here? So what I gave you is the net force. But what we're really talking about is Newton's second law. And Newton's second law tells us if you want to find the acceleration vector, there's 2 things you need to know. You need to know the direction of the net force vector and the mass. So this is the idea here. And this is Newton's second law. It relates the acceleration, the net force, and the mass. Oftentimes you see it written the other way, where you'll see that net force is equal to the mass times the acceleration. Either way, the thing I want you to know is that because mass is a scalar, whatever the direction of the net force is also the direction of the acceleration. So because the net force is up, the acceleration is up. Because the net force is to the right, the acceleration is to the right. If the net force is down and right, the acceleration is down and right. And if the net force is down and left, the acceleration is down and left. All right, let's move on to question 5, more drawing. Hooray for that. Question 5 gives us 4 boxes. Okay. Now the drawing's done. It says, if the force magnitudes are chosen properly, in which situations is it possible that the block is stationary, moving with a constant velocity? So what I like about this problem is it says which of these could be stationary or moving with a constant velocity. Well, it's a little bit of a trick question, actually. It's a little bit sneaky because both of these imply the same thing. Both of these imply that the acceleration is equal to 0. And if your acceleration is equal to 0, again, according to Newton's second law, where acceleration is equal to the net force over the mass. Again, these are vectors. But if your acceleration is 0, it tells you that your net force is 0. And if that's true, basically what we're saying is that acceleration is 0, net force is 0, and then the forces balance. So if the forces balance each other out, then we're going to have 0 acceleration. Now that could mean that the velocity is constant, or that it's not moving either way or at all, but either way the acceleration is equal to 0. So is there any way for these two forces to balance? And the answer is no. And the reason the answer is no is because this is both to the left and up, and because this is not down at all, nothing to balance out the up, so forces cannot balance here, so they don't meet either of those conditions. This one, same thing is true. We have this is up, this is to the left and up, there's no downs, so the answer to that one is no. What about this one? The answer is yeah. If you make these two the same size in terms of the force, they could balance. So yes. And this one totally could balance, because this one is to the left and up, and if this one balanced out, the right balanced out the left and the down balanced the up. So when the force is balanced, your acceleration is equal to 0 because your net force is equal to 0. So this one is 10 kilograms, 3 kilograms, 5 kilograms, and 2 kilograms. Remember, kilogram is a measure of mass, not of weight. And they are connected by cords and pulled by a force. All right, so connected by a cord, cord, cord. So this is cord 1, cord 2, cord 3, and then being pulled this way by some force, F. Perfect. So it says, what total mass is accelerated to the right by the force F? Okay. Well, when I look at this force F has to accelerate all of this. So it's not just accelerating this just because it's touching it. Actually, this force F has to accelerate everything. So the answer to A is 20 kilograms. And I know that because I have 2 plus 5 is 7, plus 3 is 10, and 10 and 10 is 20. Okay. B says, what total mass accelerated to the right by chord 3? Okay. All right, so basically we're talking about chord 3. Well, let's look at chord 3. Here's chord 3 right here. It's pulling on these three here. Now, chord 3 is doing two things. It's pulling these guys forward, but it's also pulling this guy backward. But the question is, what total mass is being accelerated to the right? So chord 3 is accelerating 18 kilograms to the right. It also asks about chord 1. We'll look over here at chord 1. Chord 1 is only pulling this one to the right, so 10 kilograms. Okay. D says, rank the blocks according to their accelerations greatest first. So this is a little bit of a trick question here because they're all connected by a string, which means that if any of them were lagging behind, the string would pull them harder. If any of them got too far, the string would go slack and they would slide back. So what I'm thinking is accelerations are all equal. And then E says, rank the chords according to their tension. All right. So tension tension is the nickname we give to a force provided by a rope, a string, a cable, anything in that can pull like that and get tight, we call that tension. So we use a capital T for tension. So here's the deal. Since they all have the same acceleration, which one has to pull harder? 3 has to pull all these guys, so it's got to have to pull harder. 2 has to pull these two guys, and 1 has to pull just this guy. So the tension in chord 3 is greater than the tension in chord 2, which is greater than the tension in chord 1. Okay, let's do question 11. Question 11 says, a vertical force F is applied to a block of mass M that lies on the floor. What happens to the magnitude of the normal force F on the block from the floor as the magnitude of F is increased from 0 to F, upward and downward? Okay, so let's break this thing down before we get started. So we have a box here, or we have a floor. We're going to put a block or a box or whatever you want to call it here. All right. So the question is, what are the forces pulling and pushing on the box? So one thing we know is that the earth is pulling it down. So this is the force of the earth on, we're going to call it a box. Force of the earth on the box. What else do we know? Well, it's sitting on the floor, so this is the force of the floor on the box. And because acceleration is equal to 0, the forces must balance. So these are these things here. Now, we have nicknames for these things. This is the force from the earth on the box. We call this the weight. Call it the weight. And there's two representations that we could choose. The book chooses this one, F sub G. F sub G means the force by gravity or whatever. So this is the force, the gravitational force. This is the force of the earth on the box. In class, we're going to use, instead of this, we're going to use M times G to represent this downforce. It's the mass times the gravitational field strength. That's what we're going to use. But how do you know that the floor is pushing straight up on the box? If the floor was slanted, it wouldn't push straight up, it would push a different way. So we know that flat surfaces flat. So flat surfaces push perpendicular to the surface. So if you were to put it here, for example, and this was your box, which way would the floor push? The floor would push this way, perpendicular to the surface. It turns out that this perpendicular idea has its own fancy physics technical word. Perpendicular is called normal. And so what we call this perpendicular surface force is F sub n. The textbook will use F sub capital N. This is the normal force, which means the perpendicular force provided by the floor. Okay. So, what happens? Now what we're going to do is we're going to take, according to the problem, we're going to take our box. And this time we're going to push, which way? Downward on it. So think about someone like pushing down on it with a hand or something like that. Okay. So let's say we have a so someone's pushing down on the box with their finger. Okay. Now the thing is, it's still not moving. Okay. It's still not moving. So what are the forces? So this is the force from the earth. We call that mg, right? This one here is the force F that's pushing down on it from the finger. But again, the acceleration is still equal to 0. So if acceleration is 0, forces must balance. So what happened over here then? So what happened was, the floor actually has to push up more to compensate for the extra down force. Think about it like being on a spring mattress. If you push down harder on it, it pushes up harder on you to balance the forces. So compared this one to this one, F normal is bigger than it was before. What happens if we were to apply that same force but in the up direction this time? Let's say we're going to tie a string on the box. Okay, we're going to tie a string on the box, and someone's going to be pulling it upward. Well, what are the forces now? We still have the same mg. The earth is still pulling it down the same amount, but now we have this up force. So this is the pull force. And what happens here? So the normal force, because you have an extra force up, it doesn't need to push up as much as it did before, so it is less. So is smaller.